Okay, so today we're going to start talking about guards, and this lecture is broken into two parts based on the heading. So this one is focused on guards. Kind of lumped in with that is handrails, and this is something that there's obviously the basic standard guard, and we'll talk about that too. With stairs, you had your basic types. Guards, there's maybe 2-3 basic types. And we'll try to look at those and a few others. I went heavy on examples in this, mostly so you could see kind of different ways things were resolved at the bottom, because trying to get the forces out of the guard is often the biggest difficulty. My husband has this, or Dave has the squeakiest flip-flops in the history of the world, huh? So the loudest flip-flops ever. So we're going to follow the usual format. We're going to talk about the strength requirements outlined in the code, what serviceability requirements, if any, there are, vibration. We'll look at free body diagrams to kind of address stability. And then I will go through some example guards. It says basic guards. Some of them aren't basic at all. It's just a really kind of good header to maybe I'll start changing that to from basic to examples. And then just some that either I found or Dave found on the internet that we thought might lend kind of a really good background or kind of opportunity to talk about something, or some of them just to show you. To be in the right spot there. Okay, so the latest edition of the code, which is the National Building Code of Canada 2015, which really didn't come into effect in Ontario until the Ontario Building Code says to use it, which is normally when a newer Ontario Building Code comes out. And so we've been using the Ontario Building Code 2012, which referenced the National Building Code 2010. It's 2010 was the last building code before 2015, right? Yeah. We've been waiting for years for the new Ontario Building Code to come out, mostly so that some of these changes in the 2015 could be adopted, because we can see that they're coming, but we can't use them. And it really starts to muddy the waters if there's some changes. So what the Ontario Building Code did was, rather than issue a new building code, they just issued an addendum that said you can use the National Building Code for all of your values now. So on the 2015 is now applicable. And in the past versions of it, everything about handrails was in Part 3. It's now been moved over to Part 4. To the point that I was completely thrown when I went to look up all of this information in Part 4 to put in this, and then I knew I had to go look at Part 3 to find that information for you, and lo and behold, all the handrail information is now in Part 4. So a guard is what you would have when it is preventing you from falling to injury or death. And so it has to be able to resist the load of somebody kind of tumbling and falling and banging into it, or actively trying to bust it. A handrail, alternatively, is just the thing you would use to help you walk up the stairs. So it doesn't have as rigorous a load criteria. They also have different kind of height outlines. That information is very much in Part 3. But guards are usually at 3 feet, right? The guards are at 3 feet. 3'6". Sorry, yeah, 3'6" above grade. And so it doesn't matter if it's taller. The point loads or the line loads we would use for a guard don't have to happen higher than that. There are other things that can impact the load on a guard, though, that could end up governing. So I'll talk about that in the next slide. So there are all kinds of different load criteria for guards, and they all have to be modeled as separate cases. So these don't all happen at the exact same time. If you guys remember, when we did load combinations, you would have dead and live or dead and snow, and we'd have live from all over the building if there was a column. We do not have to do all of these load cases, so I often number them load 1 through whatever, or I'll give an explanation in my load case kind of what it is. So there are, so we're talking now outwards. So pushing on the guard outward, you have to do a 1 kilonewton point load. But look, I have an asterisk here. The load might actually be several different load cases to test the worst case for different elements. If we have posts at discrete spaces with the top rail, the worst case for the post is a 1 kilonewton point load right at the top of the post. The worst case point load for the top rail would be right at the midpoint of the top rail. So already just that outward 1 kilonewton point load can have multiple load cases. We also have to check outwards a 0.75 kilonewton meters. So every meter of it is seeing 0.75 kilonewtons, but we do that along the entire guardrail simultaneously. This is basically saying you have a bunch of people pushing on the guardrail at once, but they're not all pushing at their worst maximum effort. I'll talk about effort and load in just a minute. Actually, I think I have that. I'm pretty sure I have that in here. Inward, we don't have to do quite as much of a force because you naturally would lean on a guardrail or fall into a guardrail. Inwards, the risk is less, so the load we use isn't as high, and it's less likely that you would do that action. So it's only 0.5 kilonewtons inward. I usually just use the 1 kilonewton. If my guard behaves the same in both directions, I would just ignore that. This might change if you had a tension only member somewhere within the design of your guard. And I'll show you a guard that might make a difference in how you design this. And then 0.375 kilonewtons inwards. So basically what it says is half of the outward force. To be explicitly, it says half of the outward force. I do love Halloween. And then downwards is 1.5 kilonewtons per meter. That is essentially assuming you have a bunch of people walking along the top of the guardrail. If you've ever been kind of out behind the bus depot area of the GO station at Union Station, you will see that all of the top rails are bent downwards where people have clearly skateboarded or walked along them. The handrail live loads are slightly less. In any direction, you need a 0.9 kilonewton point load. So look at that. Inwards for a guard is only 0.5 kilonewtons, but for a handrail, it's 0.9. So you would assume that this always governs, but this happens at a lower point on the height of something. So if the post is doing dual duty, and then 0.7 kilonewton meters in either direction. Most of the time, the guard and the handrail are part of the same component, and it's less of an issue. I'll show you my Senate project where the guard was actually a discrete element from the handrail. Just wanted to see. Okay, yeah, so I do come back to that. The other big thing for guards, and it's not obvious, it's not intuitive, that wind load can govern. Inside, probably not. If it is a regular rect style guard with the top rail, bottom rail pickets, probably not going to govern. But guards that are a solid plate of steel or wood and outside, wind can very much govern, especially if the guard is higher than it needs to be. So you might have your guard forces applied at your guard height, but the actual height of the element is taller, basically making it act as a wind wall. This is a slide or an image you wouldn't have seen in basic structures because we didn't delve too much in wind. We talked about it. We looked at how wind was applied. Also big changes in the wind section of NBC 2015. We're not going to get into that right now. But this is specifically about wind on walls. What does it? So freestanding plates, walls, and billboards. So you can have one that's up in the air. So maybe you have a wall spanning between two things, or the side of a... I just heard a thump. Thank you. It's very early in the morning and our kids are still asleep. And take the squeaky shoes off. And I wouldn't normally record right now, but I very much wanted to get it done and out of the way. If we check on them just after they wake up, they'll go back to sleep. If they wake up too much, that's the end of it, and then you'll all get to enjoy them for the rest of this lecture. So the side of a bridge that has a guard on it, for example, if it's a plate guard, or a pedestrian bridge that maybe has a solid wall side on it, this would be a really good application for it. If it's down on the ground, we would have this. So you could see that it's freestanding, connected to the ground, and depending on how long it is relative to its height, changes what some of the components are. It's a very similar equation to the basic wind one we did for buildings, but instead of CP, it's CF, and CF is the force coefficient for walls, and it or whatever specific application it is. And so you can see that this value varies. So CF comes straight out of these tables and is very much related to the height versus the length of the wall. Importance factor differs for ULS and SLS, so we kind of usually keep it at 1, but then we have our combination factors for strength, and then for serviceability, we have an importance factor of 0.75 for wind. The gust factor varies depending on what type of element you're doing. For a building, it's usually 2, but it's often hidden and embedded in that CPCG coefficient, which is slightly less applicable now because the criteria to use that particular diagram that I showed you guys in Structures 1 has changed somewhat. But often it would be about 2. If you back calculated it out or did the other methods, it's about 2 for the building as a whole. For a guard or a fence, gust factor of 2.5 would be correct. So those are the same gust factor we would use for cladding quite often. Exposure factor, basically the higher up something is, the higher that exposure factor is. So something that's less than 6 meters tall, it would probably be about 0.9. But if it's, so most of our guards, it would be 0.9, unless the guard is, on the 7th floor of a building, and then we'd need to look at what that CE or that exposure factor is. So serviceability, and this often comes up with architects, kind of asking, we don't want our guardrail to be too wobbly. And fair enough, that freaks people out when you lean on a guard and it's wobbly. There is not much in the code about deflection of guards. The only thing we really can find is that glass guards have a limit of 40 millimeters. So at 3.5 feet up off the ground, that guard can move more than 1.5 inches. That obviously freaks people out. So often we'll tighten it up, but when we tighten it up, we also find architects tend to get upset that the elements are bigger than they're expecting. So most guards are designed with that, somewhere around that criteria, or relatively large allowable movements. The thing to really note is that that force that we're talking about that creates that load is 1 kilonewton. 1 kilonewton is 1 Arnold. Trying to pull on something using your own weight is really hard to get 1 kilonewton of force. We have a kind of a meter with 2 kind of carabiners on the end that we'll actually use to test guards. And it is a very difficult effort of, have you been able to generate the 1 kilonewton on your own?
Always with a come along.
Always with a come along. So, connect that gauge up to actually like a strapping, and ratchet it tighter. What have you been able to generate just by hand using that when you can actually judge it? Do you remember how much you were able to generate?
100 pounds maybe.
Yeah, so 100 pounds, which is less than half of the 1 kilonewton. So as much as we can say it's allowed to move 40 millimeters under 1 kilonewton, it's almost impossible to generate that force with one person kind of doing that work. The code for human activity, so basically not the labor laws, indicate that people don't have to pick up anything more than 66 pounds. If something is more than 66 pounds, you need that many people to pick it up. That equates to about 0.3 kilonewtons. So if we kind of rationalize that out, that says that about 12 millimeters of movement under that 0.3 kilonewtons is the equivalent of the 40 millimeters under the 1 kilonewton point load. So, you'd see only about 12 millimeters if somebody was trying hard to move that guard. And I think if you're falling into the guard and it's saving your life and it moves 12 millimeters, I think you'd probably be okay with that. Most everyday usage, you'd move a couple millimeters tops. It's funny, we always kind of joke that the best thing you can have for your guard is for it to be flexible. That doesn't mean not strong enough, but flexible. If somebody leans on a wobbly guard, they back away. They don't want to touch that guard. It's not the methodology we use in design, but we do reference that sometimes to architects, just to kind of explain how this, even remote criteria that we actually can't, the only thing we can find is something in a glass standard that talks about this. There was rumors and chatter about newest codes having something about deflection criteria for guards, but I found that it references another code that just references that the guard shouldn't move too much. So any criteria I can find is just not too much. If we did the L over, let me just see this for a second. If we did our L over 360, which would be L over 180, we're allowed 5.9. I'm going to add that into this slide here. I'm going to add that in here. L over 180 is 6 millimeters. That is a ridiculously tight standard for a guard. They often don't have finishes that can be damaged. And people would be, honestly, architects would be outraged if we tried to design it to that type of a criteria. So often I will discuss this with the architect and let them know the lower and upper bounds of what it is, and then what the actual criteria is. To be honest, most guards that I end up designing just to make them match, because architects often have the idea of exactly what they want in their guard. Usually I'm not generating the sizes, but often checking that the sizes they want to use work. And typically when that happens, for a 1 kilonewton point load, I'm often getting deflections of 8 to 12 millimeters. So, well under that 6 millimeters if we were talking about our 0.3 kilonewton movement. Vibration doesn't really apply to guards. You might see it be a criteria if your guard is part of the stringer of your stair, then it would become very, very important. But you'd want to make sure you weren't looking at the vibration of the guard, but the actual movement of the stair or the stair, not the guard itself, because that would be a different vibration. And often we're using three-dimensional software analysis to determine what these vibrational modes are. So you have to you can't just pull a number out of the code. You have to look at the movement and the behavior of it to see if it actually is a movement that you're concerned about. So I just wanted to show you a few free body diagrams that we would see for a stair. So here is a guard with a height And this is pretty standard. You'd see this for glass guards, ones with pickets that have just a base plate anchored down into the ground. I didn't draw every single version of every single load case, but I just wanted to show you. So that this would be the 1 kilonewton point load, or the 0.75 kilonewtons per meter, or the 0.5, the 0.375 going in the other direction. So we have a load applied here, and we need to resist our 3 degrees of freedom for a 2-dimensional analysis. We have a reaction here stopping movement in our x-plane. We have a reaction here stopping movement in our up and down plane. And we have a moment reaction stopping rotation. I've always said how moment connections are a pain in the ass and hard to build. The forces we're talking about in guards are quite nominal, but this really is where kind of the biggest part of the guard tends to happen, is at the base, trying to resolve that moment or detail that moment. And I'll show you examples of what those look like. Here it is with a wind load. Same free body diagram is applicable. Point load downward, same free body diagram is applicable. We could do a different way to resolve this moment. If you guys remember force couples, where 2 forces in opposite directions, equal and opposite forces, the same distance away from a centroid, or change those values with different differences, can be the equivalent of a moment. So an applied load up here can be the equivalent of these 2 forces here to take out the rotation. And it's what we did all the time in beam analysis. So instead of a moment resistance, we're using a force couple to make sure we have resolved all 3 degrees of freedom. We have our y for up and down. We have 2 forces in x, and we have our x1 and our x2 to resolve the couple as well. So let's just talk about stair basics and the stair basics of the names. So the general guard would be the entire thing down the side. That would be generally what we're talking about with the guard. The posts are the bigger, if you have them, the bigger discrete elements that are some distance apart. They're the ones that would connect down to whatever we're connecting it is, whether it's a stringer, whether it's concrete, whether it's a steel beam, but that's where a moment connection would happen for this. If we had a plate guard, we would have something continuous happening all the way along. Top rail is where we're going to apply our guard forces. So that's got to be 3.6 feet above what we're looking at. Bottom rail, less structurally important. There are some, actually I wanted to go back and look at this. Individual elements within the guard, including solid panels and pickets, shall be designed for a 0.5 kilonewton point load over a 1 kilonewton by 1 kilonewton, or a 4-inch by 4-inch area, or a 100 by 100 millimeter area. And so that's what we would use to design a picket, but also to design a bottom rail. Now the bottom rail might also be working coupled or to make a deep beam with the top rail for that 1.5 kilonewtons per meter up and down. You know, a kicking force, it would want to be designed for that 0.5 kilonewtons as well. Pickets, we would want to look at that 0.5 kilonewtons applied at the midpoint of one of them. And then the handrail, is usually at what, 3 feet exactly? What?
The posts? Oh, the handrail, yeah.
The pickets can be at whatever space in it. 4 inch, yeah. Sorry, the handrail's at 3 feet, right? Yeah. So 36 inches is where your handrail is, but our guard needs to be higher. So that's why you might, and if this is discrete like this is, it's pulled out, we also need to check this for its load. And then you could imagine that if this is the handrail and this is our guard and we've got that downward force, it tries to tip over our guard as well. So that's another load case that we have to look at. Well, I'll come to that in just a second. So there are all kinds of common guard assemblies, and there's also all kinds of uncommon ones. It's kind of less hard to say what's normal. I have pulled out some normal ones, and the very first one is where I'm going to talk about some of the extra criteria. You could have a hidden guard, so that might be something in a house where it's kind of embedded in the drywall. We have one built like that here in our house. You can have one exposed. We never took pictures of any of our guards that we've built.
No.
Mostly because we didn't design them to code. You can have glass plate, steel plate. You can have wood plate as well. Steel and aluminum built up. Those are often quite standard looking, probably the ones you're used to seeing around the outsides of buildings. And then you could have solid concrete as a plate. I'm going to add a slide of common dimensions. I think you guys might benefit from that. So I'm going to add a slide of common dimensions. This image is not, I'll add it right around here somewhere, maybe back a little bit. This slide is not our code, but it did reference some really good things. So here, this one, it says the guard height is 36 inches. For us, it's more than that. It's 3.5 feet, so 42 inches. Our handrail is at 36 inches. A stair guard height, this isn't really applicable for us. I might just delete all of this stuff at the bottom, but it's a good place to kind of start the conversation. The big one is the pickets, how far apart the pickets are. The idea there is it has to stop a 4-inch ball from being able to push through it. There's actually another load case I wanted to add. A ball passing through it. That ball is really representing a baby trying to get through it. Our first son had the biggest head in the world. It wasn't something we had to worry about at most places. But what we're trying to worry about there is a baby getting through the pickets. So they say a 4-inch ball. So that opening between the pickets can't be more than 4 inches. Often people just space their pickets at about 4 inches on center, and there's some width to those pickets, leaving a slightly less than 4 inches in between them. They're also, if those are very flexible elements, they need to not move so much that under a specific force that ball can pass through it. And I can't remember, I just found that information and meant to add it into this slide. I'm going to go find that again. I'm going to add it into the load criteria, and you'll see that there. So for you, these slides might look a tiny little bit different, but I'm giving you all the data and you'll see it written out. This particular place said that they gave you a direct criteria on how much those pickets could move, but that's not really applicable for us. And then they varied what the opening could be. Kind of a weird thing for this. So you guys, I'm going to cut most of this off because now that I look at it, it's really, really, really misleading. But this is why I know a lot of people got upset in years past that there is no book for the structures curriculum. And that's because everything is written to the American code, and the American code has a bunch of different codes. There's the International Building Code as well, the European codes, the Australian codes. The ones that apply to Canada alone are really just the building code. So there's no textbooks that really kind of address the things we need to talk about. I would have had to make you guys buy like almost $3,000 worth of textbooks to kind of grasp everything we needed to and then put heavy caveats on, this is what you're taking from this one, but ignore everything else because it's not applicable to us in Canada. Here is a basic deck guard built into some other stuff. So this is from the TACBOC details, which are basically, if you want to build it and you don't want an engineer, you can look at these details and it will give you ways to build things for a house. It doesn't deal with all things, but it will help you avoid the cost of an engineer. They're quite robust, and it's often what you're used to seeing kind of in residential housing. So you can see here, this particular outdoor deck guard has a 4x4 post, or an 89 by 89 post with pickets at some spacing along it. They said here 1.5 by 1.5 pickets. They have a continuous top rail. Our code has some criteria about top rail. Our code currently says that you have to have a continuous top rail. The idea being there that if something fails internally, you still have something at the top to protect you. That is why glass guards often have that piece at the top. If we had no top rail, if a glass panel failed, you have nothing to prevent that opening at the top. Glass guards, we've seen kind of incidences in Toronto where glass guards have spontaneously failed on some of the high-rise condos. So if you didn't have a top rail, you'd have the possibility of somebody being able to fall off there with absolutely no protection whatsoever. I'm thinking of all of these things now that I'm talking about it that I want to add into these slides for you guys. Standard glass guard. These are almost always designed by the proprietor or whoever the particular designer of these guards is. A base building engineer will often design what the guard is connecting to. If this was embedded in concrete, they'd design that. If this is being fastened down into something, you can see this detail here shows something being screwed down. Well, we design what it's being screwed into. The glass would be designed by the supplier. That's not to say we can't design glass. It's just they've basically done it a million times for guards, and it wouldn't be efficient or cost efficient for the owner for us to do it. That said, when there's unique conditions and complex conditions, the structural engineer can definitely do it, or certain structural engineers can definitely analyze the glass for a guard. And we're going to spend a whole lecture talking about glass design later in the term. You can see different top rails that would have to be continuous, and you can see conditions where the handrail isn't at the same spot as the glass guard. This condition here, I didn't draw this free body diagram, but this one, instead of the couple being like this, the couple is like this, or if you wanted to draw it like that. As somebody's pushing out on that top rail, it tries to push down there and tries to pull that screw up. The load is different in reversal, and they've actually designed that as a moment in the reverse condition. Here's the detail at the base for that couple, the way I drew that other free body diagram. So let's start looking at just some basic examples, and then I'll get into some project examples. So here's a plate steel guard. You can see this stair is actually really cool. It's actually bent metal, but it's perforated or a mesh, so you can actually see the guard underneath it here. So this is just a bent steel plate of some thickness. They've had to analyze this with the couple coming out through this stair. So it's being resolved by connecting into these stair treads as its couple, transferring the moment into these stair treads, unless there's a hidden stringer that I'm unaware of. So it's trying to bend, it's got a reaction at the base, it's also acting as the stair stringer, and that 1.5 kilonewtons per meter downward load on the plate guard. So it's doing a lot of work. There would have been a lot of different load cases to look at here. This one has no handrail because the handrail's designed on the other side. So not every guard has a handrail. I wanted to also mention height when we have it, the guard. Oh, it's going to feel so nice to make that slide, and you guys are going to be absolutely baffled when you see it and then see me ignore it, and then hear all the information come out through the lecture. We need a guard when we're adjacent to something more than 2 feet off the ground. So if we have more than 2 feet off the ground, we structurally need a guard. So you're doing landscape work and you've got a curb that is 1.6 meters down into something below, no guard needed. You have something more than 2 feet, you're going to need a guard at the top of that. There are some loopholes about building kind of benched seating down off of steps that can get you away from guards. But if it's over 2 feet, the standard practice is that you're going to need a guard there. Here's your basic, kind of most basic guard assembly. You can see that there's a moment connection here that they've covered with a cap plate because there's some base plate there. They have connections in here that they've hidden with clips to kind of hide that connection detail. We've got a top rail, bottom rail, pickets, posts. We can do concrete guards. Well, this one here is actually a cast-in-place concrete stair that has the guard acting as both the stringer and the guard. You can have really heavy-duty guards. This would be for vehicular loads, which is not what we're talking about in this course, but I wanted to show you, when I searched for some concrete guard images, there really wasn't any, but a ton of the vehicle ones came up. So I just wanted to show you that there are other guards that might be above and beyond what we're talking about. But this would be designed for a car impact, which is often we're directed to design that it wouldn't resist the car load. It's expected to fail and deform when it's hit, but it's about 22 kilonewtons of a point load. So now I'm going to show you some drawings and just talk about some precedent projects that I worked on to kind of give you a hint and a taste of some different guards and what those look like and kind of the iteration and the thought process. Some of these go back quite a bit. Some of them you're going to see that instead of the 0.7 or instead of the 0.75 kilonewtons per meter, I used the 1 kilonewton per meter. That was more because I had a factor built into my modeling software, so don't worry about that too much. So here's just a basic one. This one, a fabricator literally called me up and said, we build these all the time, but we need a permit. Can you back engineer this for us? So it's a quick, small project, not a lot of work for me. Interestingly enough, they didn't need it as a guard. It's not 2 feet above anything. So it is literally just a railing. It was more of a visual divide. People would probably lean on it. But it didn't need to meet the requirements of a guard. But what I decided to do was say, okay, there is no criteria really for this, but maybe handrail criteria. So I made the choice to design it as a guard with them, because they already had, actually, I believe it was already built. I wanted to see where it deviated from what it would meet for guard criteria to basically give me a sense of how outside of the range it is. Understanding that it didn't need to meet any criteria. I forget why they needed it signed and stamped. I think it was because it was in their contract with the owner, even though it had no criteria that it needed to meet, and that's why they went and built it. And then in the spec, it said they needed to provide signed, stamped shop drawings, so they were in a bit of a pickle. But the signing and stamping could have just happened. But I decided to be rigorous and say, okay, what could this meet? So I built a model in my modeling software, remembering that it's not for graphics. It is all about applying loads and seeing how the behavior works. I didn't model multiple segments because the worst case for the post was going to be the 1 kilonewton point load acting on it right here. There could have been a worst case if those were longer and the sum of half of this side and the sum of half of this side made for a worse point load on the post, but it didn't. So let's take a look at the live load cases I modeled. So there's the 1.5 kilonewtons per meter downward. I did 1 kilonewton along its length because the code does say it needs to act in multiple directions. But it actually doesn't explicitly say that. It's loosely alluded to, and the handrail code very much does. I've modified some of the ways I model this now, where I might treat that load in that direction more as the handrail load, because there is no explicit load in that direction. So I think I'd probably switch it, but it was only a moderate switch of 0.75 to 0.7. Like I said, I used 1 here because I had the modifier built into my model. 1 kilonewton acting outwards. Remember, so it's supposed to be 0.75. I have that modifier built into my model because this one I was trying to see what was happening, and I do that sometimes where it lets me play with things, kind of my standard build-up lets me play with it in the load factors as I vary between guard and handrail. Remember, we could have 0.5 inwards, but the worst case is going to be 1 outwards in this particular application. A different guardrail, then I might have a real change benefit or being worth modeling. 1 kilonewton acting downwards over here on the post. There's nothing, I can't remember if it explicitly states that or not. I find it good practice to check kind of the buckling of that element. 1 kilonewton along its length, 1 kilonewton as a point load here, pushing outwards on the guard, but at the post, because that's going to be the worst case probably for that post. And then I wanted to check 1 kilonewton at the midspan, 1 kilonewton impacting here, and then 1 kilonewton at the midpoint of the top rail, because this is bending between our posts, and so we wanted to see that. This one was interesting that they had pickets that were cables every 4 inches, but every so many of them weren't. Actually, let's go back and look at this slide for a second and see that these ones were cables that they were going to tighten to stop that ball load passing through. And then these ones were rigid poles to kind of just help tie this system together. Probably had more to do with the way they were erecting it than anything. So let's just come back to all of those loads. Here is an envelope reaction case. So an envelope is when I look at all of the load combinations, and for each load type, it pulls out the worst case. So all of these might not be from the same load combination. I need to check the worst case of every single one of those. So this pulls out the worst case of every single thing I need to look at here in this envelope. So you can see these were moment connected at the bottom. You can see that we have our reactions in all 3 directions, because this is a 3-dimensional model. So I don't have just those 6 degree or those 3 degrees of freedom I need to resolve. I actually have 6 degrees of freedom I need to resolve. I have up and down, side to side, in and out of the page, and then rotation about all 3 of those axes. So these reactions give me that. And this is how I would design the anchors at the base. And so I've modeled this as a moment, but the way we resolve it is as a couple with the anchors that you would put in the ground. Here is the analysis for all of these load cases. And you can see here there's a color spectrum at the bottom that tells us our utilization. 100% is that my factored load is equivalent to my reduced capacity load. Anything over that and my factored load is higher than my reduced capacity load, which is what we normally don't want. But you can see here I have 3 elements that indicate a failure, but this is where understanding how you modeled it is really important. I went in and I checked to see what load case that was and saw that it was one of the ones that actually isn't applicable for what this thing is doing. Remember, I modeled this as a guard, even though it doesn't really meet the criteria of a guard. And I applied some load cases, live load cases that might not normally be applicable, but I wanted to do my due diligence and see how it moved and how it behaved. So I was willing to accept this overage because it's not really an overage. It actually works if I followed the prescribed outline in the code, but I wanted to check for my knowledge base of how these things might move in a different situation. And so here is the deflection due to the 0.75 kilonewton meters at the top rail in the Y coordinate. So this is somebody pushing outward on the top of that, and it moved 9.8 millimeters. So remember, we said that under, so the 1 kilonewton point load wasn't the worst case, it was less than this. Remember, we said that 12 kilonewtons from a 1 kilonewton point load was 12 kilonewtons from 0.5 kilonewtons or 0.3 kilonewtons was appropriate. Well, this is a higher load with less movement. So totally realistic and totally appropriate. So here's another example. This one's being fabricated right now. This is Jennifer Turner, and MCM 2001 is the fabricator. Fantastic fabricator. Kind of, if anybody has ever remembers the pictures of my longhouse that I did at NCFF. Do I hear a kid? No, that was you yawning. It's like there's a time bomb upstairs and I'm waiting for it to go off. I'm hoping to get to the end of the guard lecture so that I can film the canopy one tonight for you guys. I had to get up at like 4 o'clock to be able to do this for you. And I'm living in terror that one of them is going to wake up. The MCM 2001 did the longhouse where we just gave them the 3D model. We produced no drawings, and they went and actually were able to fabricate directly from that. So fantastic fabricator. This one came to me from Jennifer Turner, and she had drawn it, and she said, I don't know if I want this in aluminum. I don't know if I want this in steel. I don't know if I want cables. I don't know if I want rods. So I went through and analyzed it 4 different ways for her, showing the aluminum and the steel and cables and rods. And then between her and MCM 2001, they determined which one they wanted to do. MCM 2001 produced the shop drawings and sent them back to me. I verified that what they did matched one of my analyses, double-checked my analyses, and then signed and stamped their drawings. Often fabricators have their own engineer, but one of my specialties at my firm is sometimes I will be that person for them. Often the architect hires someone to kind of engineer it, but not fully, and give them just loose feedback. And then the fabricator's engineer engineers it, but the difficulty there is loss of control for the architect. And so kind of one of the things my company specializes in is kind of bridging that gap a little bit. So for this one, when I looked at it, the thing people always come to us and say is aluminum is lighter, therefore we want to build out of it because everything is going to be smaller and cheaper. Aluminum is less strong, and it's also way less stiff. It is about as third as stiff. It's about half as strong, but a third as stiff. And so things that might not be a deflection problem for a guard in a steel guard can become a problem in an aluminum guard. So it's really important to know what material you're modeling with. In steel, it's important to know whether it's stainless steel or not, because stainless steel is not as strong as regular structural steel. Whenever we've talked about steel in the past, we've been talking about structural steel. Stainless can definitely be structural, but it's a different grade of material, and you have to know which stainless steel they're using, and it has a different strength capacity. It has the same stiffness though, so often you end up with a stiffer guard because you need more material. So the perception is that a stainless steel guard is nice and stiff, but it's because we need more material because it's less strong. So here was my model. This is in here as a placeholder. It wasn't actually metal. They did this as, again, a plate, and then they capped it in wood. So this one I knew that as long as all of these elements worked, this top one was going to work no problem. But I built it into my model. I added the wood to include the weight of it, because built into all of this is also the self-weight of the element. And if you look back here, they had the bit where it turned the corner, and these actually weren't connected to each other. So this part is a guard, and this part was below 2 feet, so it only was a handrail. Again, I start with the premise that it's a guard, even if it's not, and then I look to see if it doesn't work for what they're showing. And if it doesn't work, then I might go down to the handrail design. Mostly because it's nice to say, should they change their mind or the building department come back and say this needs to be a guard, my sign and stamp still works for it. If it doesn't, we would have to explicitly state that it's only a handrail on the drawings. This kind of gives, for no extra cost, the architect some freedom. So let's take a look at the loading that was applied on this. So here's the 1.5 kilonewtons downward. On this, I wanted to be explicit because they were using this as a handrail that was quite high. But this one here actually met the height requirements. So I wanted to check both the top one and the actual one for the guard loads. Again, in case I had a feeling that what they were going to do was pull this down to this height here and get rid of this top rail if they priced this out as too expensive. So sometimes I'll check what I guess is going to be a perceived problem. Again, if everything works the way they've detailed it, I'm not going to worry about it. I might give them feedback if something is very much over designed, but often they have a pretty clear idea of what they want visually. So here is the 1.5 kilonewtons modeled on the layer down. Here is 1 kilonewton acting outwards. Again, it's only, or 1 kilonewton per meter. It's only supposed to be 0.75, but that's something that is built into my model to give me freedom, where I apply it in the load combination. So I adjust my 1.5 to be 1.5 for my load combination. Remember, a factored load, live load factor is 1.5. I will multiply that 1.5 by 0.75 in my load combinations. Again, I didn't use the handrail criteria simply because this might end up being the permanent guard. And I figured if it didn't cause a problem, let's not readjust it. I wanted to check the midspan of each of these elements to see how they behaved in bending for that 1 kilonewton point load. Same for the top rail. And then I wanted to check my post conditions because this is where I was going to pull out my reactions, and I wanted to see how these reaction loads would be impacted by that and the buckling capacity of these posts. I wanted to check the top rails in bending, weak axis bending, and the posts for a 1 kilonewton point load. And then here is my picket load with that 0.5 kilonewtons that the code specified. Now that can be over a 1 inch or a 4 inch by 4 inch area. I often apply it as the 0.5 to see where we land. Remember, so this technically could be spread out over a 4 inch by 4 inch area, but that 4 inch by 4 inch area is still that one picket. So that 0.5 with a ball could push right on that one picket. So I want to really check all of the options on this. So here is another envelope of reactions to see how I need to design those connections to the concrete, because this was actually 3 of them were connecting to concrete and 2 of them were actually connecting to the wood deck. So those needed very specific details on how we connected to the wood deck. Interestingly enough, as long as we meet all these criteria for height and how far apart our pickets are spaced, I can reference the tack box details for what that connection looks like actually embedded in the deck itself. So here's the strength analysis where even with my my application of guard loads, even on the handrail elements, it was well within the requirements of what the architect wanted to do without being over on strength at all. And then here is what my deflection looked like. So this is the 0.75 kilonewtons per meter at the top, and you can see that our worst case is 8.25 millimeters. The handrail portion is even less, so we're well within kind of even those loose criteria, and we're actually starting to get close to what the if you wanted to do the normal building criteria of L over 360. This is a cantilever, so it would be L over 180. We're almost at that criteria, in fact. So this one's interesting. They came to me and said, we have a guard that we have to put around our building's property. And it's being attached to an armor stone, which is basically stacked stones, retaining wall. So I looked at it and realized that the way they were building it, it was essentially a fence. It had to meet the guard criteria, and that's how they were talking about it. But the wind loads are actually what ended up governing this design. It was an interesting process because we couldn't just hilty into this one stone because there's nothing connecting these stones to each other. As this tried to rotate, the couple that I would normally do into concrete, for example, which is just 2 anchors resolving that couple, would work. The fence would be securely fastened to this stone, but the stone would tip over. And even this stone would tip over. And even these 3 stones would tip over. We had to drill down to engage these 4 stones to not tip over. Interestingly enough, I specified on the drawings what loads they needed to include in this armor stone design. So they had their surcharge, they had their soil load, and they needed to worry about the overturning because I wasn't designing the armor stone. There was pushback from the armor stone people saying that these wind loads that I had used were not what they calculated. And so when I asked them to provide what their wind loads were, they weren't following the code. So there was some back and forth about that, where they just flat out said I was wrong. I provided calculations, signed and stamped. They wouldn't provide their calculations that said I was wrong. The owner was frustrated, the architect was frustrated, I was frustrated. So I had a call with the owner and explained that, that this is for a 1 in 50 year load. You could probably argue importance factor, made it a low importance so we could reduce the load somewhat, and said that I was happy to sign and stamp my scope, but that they would need to communicate with the Armorstone people for their scope and the own. And so it's not my job to tell them that they're wrong here. I can provide all of my information. They're ultimately signing and stamping this. I didn't think it was an unsafe system. Realistically, the worst case was a 1 in 50 year storm while this surcharge, so basically someone would be having a party out beside this retaining wall during a hurricane. And so we talked about the kind of level of risk, and I said it's not my job to argue it. I just want to let you know what my calculations are showing, but they're signing and stamping it. So in the end, they accepted the Armorstone people signing and stamping this, and me signing and stamping this, even though the Armorstone people said they did not design this to my loads, and the owner was happy with that. Again, I did not perceive a life safety risk. Otherwise, it would have been my responsibility to take that further, even though it's also not my job to question another engineer. I have to allow that engineer to know I'm critiquing them. That's part of the kind of code of ethics that we have. So before I contacted the owner or architect, I did have in-depth conversations with the Armorstone people and let them know what I was seeing in their lack of calculations, because they wouldn't provide it to me. So here are my drawings for this. So this was wood posts with slats spanning in between with kind of edge pieces that they connected onto at the posts. I resolved this. I had them create a shoe, so a steel plate saddle that they shaved down the I think it was a 6x6 that we ended up with. Yeah, 6x6 that they shaved down to get fit tight into that shoe. And then that had an anchor welded to the bottom on it that was cored down into the Armorstone. So 4 layers down into the Armorstone. And the post resolved as bearing at the top of the saddle and bearing at the base of the bottom of the saddle. And the shoe resolved in bearing right here on the shoe and pull out of that epoxy anchor into the Armorstone. So here was, because I had to produce a calculation report to provide to the Armorstone and the people, and Armorstone, that's a company name. That just tends to be the name for it. I don't think they were literally the company Armorstone. I wanted to provide a detailed calculation report. And remember, wind load very much governed this design to the architect and the owner, as well as the fabricators of this retaining wall. So even with low importance wind loading, the wind governed. And so you can see here that I used the wind load on a wall, which was the appropriate thing to do. The CE was less than 0.6, even less than 6 meters, even in counting for the fact that this was the full height for this analysis. And so I provided my VF and MF that were posted on the drawings. So I already showed you this, so I'm going to brush through it a little bit. So here are my drawings. There was 8 different guard conditions on this building, and the glass had already been designed by the glass supplier. So that wasn't my scope, but often you can see that's a kid. Be quiet in case it's Duncan, he'll go back to sleep. Here is, sorry, that's like an hour earlier than I wanted him to wake up. Damn it. This shoe, remember, it has a screw that goes down into it. It needs to connect to something that can still resist that moment. So this one here, this was a placeholder for more detail, and I have a model of that I will show you. So this connected down to an angle that spanned between basically outriggers that connected back. We created a frame system here to resolve that couple. So you can see that. So this one here, they actually ended up adding a bit at the top as well. So they had a low guard, lower than what the code met, and that was okay for the application they had. They had a whole, it was the architect had a whole complex method for when and where the height, what the heights needed to be. They just told me to be consistent with the guard load applied to the top. In the end, I think it was this one, ended up needing the Senate building owners ended up changing their mind and wanting that addition put on top. And so I'll show you that further down. So this is one of the details that we did. Where I couldn't put the outrigger back because we had a steel beam, this was the detail that we provided. Again, I always say we, but it's just me. I don't know why I say that. With an HSS stub down to resolve that moment, taken out into the decking that's resisting the load by the uplift of the weight of the deck. Here's one where we had HSS stubs down. So everything in the light gray was already there by the base building engineer. So we added these HSSs where instead of the shoe being screwed down here, the shoe could be screwed into the side of the HSS. This is actually the stair stringer itself. So this one I had very good control over. So this was the stringer of the stair, and this would get anchored down here. This is the inside stringer. So this was the one that was working harder, that had the big loads on it. Here's the HSS stringer. And then these were LVL upstands every couple feet with an angle on top, and then they built the rest up out of plywood. Here was the overall handrail design where they had, so this was originally to be designed in bronze, which was kind of fun. So I found all of the bronze analysis. I designed it in bronze and my drawing said bronze. In the end, they wanted to change it to steel, but not the structural grade steel. They had kind of other steel they wanted to, and then they wanted to do this alternate aluminum that had different properties than the normal aluminum. So in the end, what I did is I took the bronze material properties and I said they could design it out of whatever they wanted as long as the material met the strength requirements and the stiffness requirements of the bronze that it was originally designed with. So there were details on how to make this look seamless. So these were tubes, 2 tubes that then had a solid plate in it that these shafted over, and then they had pre-drilled screw holes. So it was basically like designing fine furniture. And then these handrails were wrapped in leather afterwards, where the end bits were exposed. This was a handrail that they realized later needed a guard added to the top of it as well. So this was a guard plus handrail condition. This was a condition where they wanted to be able to see through, but also have it be a guard at the top. And so the way people might come down, they wanted this to be as open as possible. So again, I wasn't designing the glass, but I was designing everything that would take the glass. This was one that after things were pretty far along in construction, they realized they had that the fabricator who was building the built-up podiums used a different method than they had originally anticipated. So they had originally anticipated that this would connect directly to the built-up kind of assembly for the seating on the upper floors in the gallery, but they couldn't do that. So they now needed something that could pick up this guard, but they now needed to connect it really far down. So look at this, we're 1.6 meters down. So what's that? Over 5 feet? Yeah, 5.5 feet. So much higher than the places, the amounts of loads we normally apply. These elements by themselves were not strong enough to do it. So what I suggested was build what they normally were going to. They had already fabricated this, in fact. And then I told them to provide a 100 by 19 HSS that's anchored down into the concrete slab down here. You can see that detail there. And then they came along and fastened their posts directly to that HSS. So it's almost like the guard only goes to here, and then we have really stiff, strong upstands picking up the guard, or this was actually a handrail at that point. And then I told you that there was a condition where there was a glass guard that they wanted to come back and add the actual proper guardrail height to the top of it. So this is what was built. So this was already installed, and they wanted to bring it up to here, following the same kind of look of the other options. So I gave them a few options. I said we could have a continuous rail of this size. We could have a discrete element at certain points that would be bigger. We could move this in and bring it down and have its own have its own connection beside it. In the end, they opted for this. So it was a continuous, basically what the glass shoe is like at the bottom, upside down on the top. Now, the glass guard people didn't want to get involved in this. So what I did is, based on their analysis, I went back and looked at the worst case loading condition, because they had this guard in multiple spots that did come up to the proper height. All the same shoe design, all the same glass design, so no change in it. I had access to their shop drawings. So I back engineered what the worst case point load and stress in the glass was for their other conditions of analysis. And then I modeled it using this to see what the worst case local load and overall load and stress would be on the glass. And if I didn't exceed their conditions, I was able to sign and stamp it. So even though this was shorter than the other ones, it was built the same as the other ones. And so as long as I didn't exceed the stresses of the taller ones with this analysis, we were fine. So here were the loading conditions for the Senate building. Here is that condition I told you about where I brought back outriggers. I'm not going to show you all of them. I just wanted to show you a couple. So here's the outriggers coming back. So this is what my model looked like. This is the graphics are not great on this software, so it's really just about analysis. And normally I don't even work in this mode. I work very similar to what it would look like when it was a free body diagram, just simple lines, so not this kind of three-dimensional look to it. So here is the guard. I wanted to show you this because it's kind of interesting. Here is the guard, the glass guard with the shoe, and the top edition, the upstand edition that I modeled on it. So I just wanted to show you my analysis, or just some of the images from the analysis of how I went about that. So I applied all of my guard loads on the top, and then I ran the analysis to see what the stresses would be. So this glass had a shoe at the bottom, but it also had localized anchors along the top. So you've seen those ones that kind of go through the glass. And then I wanted to look at the worst case spots and see, as I broke down the analysis, or basically became finite element analysis, what those stresses were. And if they were reasonable and less than what we would expect from the basic taller glass guard, then I was okay with it. So this was one load case. Here was another load case. You can tell this one was probably from the 1 kilonewton point load added right here, where my worst case stress was right here. Here it is where I put where it was at this point. Here are my handrails. I just wanted to show you the model. Here's the structural analysis. And then here they are erected. Assiniboine, I've shown you this one already too, so I'm going to start to go through it a little bit faster. I didn't want these lectures to be longer than an hour and a half to kind of add up to the 3-hour kind of total. This is what we were given, what I was given for the mesh panel here. When I did this, I looked at kind of the spots where they had the most material removed and saw what the equivalent of that was over a similar area. So what the equivalent thickness would be for the entire cross-sectional area or the entire volume of that element. And so they were, I think, using 3/8 inch plate. Yeah, 3/8, I believe. And I ended up modeling it as 1/8 inch plate for the analysis, knowing that they were taking out so much in the worst case with perforations. So here is what they gave me for their guard material or their guard design. You can see that it needed to be erected in stages on this curved element. They had essentially discrete panels of it. They had 2 levels of handrails for children and adults. They were connecting into the stair stringer that I also designed. And so I needed to keep that into consideration of what that analysis looked like. So here was the model of my guard. Again, I didn't want to show you too much on this. I just wanted to address it. So this one's really, really cool. So this was Williamson. So you guys all know Shane. He was the director of the ARC program, and he's on sabbatical this year, which is also his last year to be doing it. So they came to me with a problem that they had a roof that is now, that was always an exposed roof. It had lots of strength, but now they wanted to make an outdoor deck on it. They wanted to access it. So they had put a nice big slider door in there, and they wanted to be able to go out and access this deck. The problem is, and this happens a lot, one of the biggest issues for structural rot in wood is piercings in the roof membrane. It tends to be one of the biggest places for flaws in a building. So anything you can do to not pierce a membrane is exactly what you need to do. Williamson said, we cannot pierce this roof membrane. Whatever resists these guard forces has to not touch the building itself. It has to be self-resistant. So that moment that we'd normally have at the base of our guard had nowhere to go. So this is a glass guard. I'm not doing the glass itself, but we've all seen that this is pretty standard and we know exactly what it's going to be. We had the opportunity to hide anything I did here, and I had some room underneath the deck to hide whatever we did. So this is what they came to me with, and they said, what can you do for us? So I said, well, one thing we could do is resist that load into structural members, but we didn't have a lot of depth. We had to stay underneath that decking, which had to be where it was because it needed to be near the door opening height, which was already there. So we needed to drop, we had to keep everything underneath that roof decking. So it needed to be razor thin. So we came up with the idea of getting plate steel and cutting openings in it. Hey buddy, can I have a hug? Good morning, do you want to say hi to all my students? Hi. It's still dark out and he's awake. We said we can build it in steel plates and cut it out just to get rid of some of the dead load, because We didn't want to have all of that steel weight up there because the steel's really heavy. So we wanted to cut our weight, and we didn't want to create a drainage problem. We needed water to be able to drain down underneath this and get out through the roof system down into the gutters. So those were all the criteria we had to meet. One big piece of steel this size, even with the holes cut in it, A, would be too wobbly and floppy, and B, it was too heavy to get up on site. So we cut it into sections and then came up with, so this was laser cut, so it was a solid piece of steel with these openings laser cut out of it, and then out of those pieces, because they'd already paid for that steel, was cut again to make basically clips that went underneath that had pre-drilled holes that they screwed these assemblies together. So this was my model. Remember, I'm not modeling the glass, and this is my modeling software, which is not exact graphically. And I needed to look at a few different conditions. Like if I had put the guard over here and modeled my outward forces simultaneously, I would double. Basically, I needed to make sure I didn't have things helping me when I needed them to hurt me in the analysis. So the weight of that was actually helping me somewhat. And I needed to see where these loads dissipated. Where did this stop trying to lift my steel assembly up? So here is one of the models where I had a live point load at the top of the glass, and I wanted to see how this steel behaved. And I wanted to check and see how much, because now we're connecting into something flexible. So that guard, as much as it can deflect, if it's connected into something flexible that can lift up, that can amplify the deflection of the guard. So I needed to check how much the top of this guard moved, including the rotation of my base assembly. And so you can see these ones here modeled this way. I had to model this twice because I didn't want this and this impacting each other, and this just made me have one load condition a little bit easier. Here it is with wind on it, because wind actually was a solid glass wall, makes it a wall. I didn't have pickets that wind could get through. So this ended up being the governing case. You can see for wind on this outside face wall, my steel actually arching up. And so this arching needed to stop by the time we got back to this weight. That any uplift, that this wasn't trying to flip up in the air. If that was trying to flip up in the air, we had a system that didn't work. So this is just wind itself. The model that shows self-weight and wind would show that this was flattening out here and that rotated right there. And so eventually the weight of this was enough to keep it held in place. And then these were the structural drawings that they were given, where I showed the individual panels that were being lifted up onto site and the sections that were cut out. And these were cut out to make sure they would fit out of these bits here, indicating the dimensions and sizes. And you can see down here at the base how that fit in between the deck and the existing roof, using those clips to kind of pre-drill it. What's great about this one is Betsy was able to go find me images before they covered it up with the deck. So here is that steel plate. You can see the connection elements under here. It looks like what they actually ended up doing was, rather than drilling two of them, they actually brought the plates already welded to the underside of these ones, so they only had to connect it once. And so you can see here they've got the shoe detail and the glass guard going in, and they're getting ready to put their decking on top of it. So you can see these ones were welded to it, and then these ones were screwed down. So those were all of the kind of practical ones I wanted to show you. I'm just going to quickly go through fancy images of other guards. Some are ones I've worked on, some are ones Dave's worked on. And then some of them are just ones that I found on the internet to try to show you kind of the range of them. Where I can, I found who they were designed by. So this one we looked at before. You've seen now that it's not, guard-wise, it's not that fancy. They have their pickets, they have their top rail, they have their posts, they're connecting into concrete. You can see where they make the switch to handrail because they're less than 2 feet above the ground, and they don't need to meet all of those guard requirements. They just need to meet the handrail requirements. This is the one that Dave showed you that he did. So this one, we've got a handrail and top rail. We've got our posts, our pickets, our cables. So this, you can see that that's 4 inches and that's 4 inches. They actually did this at tighter than 4 inches. And those cables needed to, when you tried to push a ball through, not separate so much that the ball could go through under a specific load. Buddy, Daddy's gonna come in. It's okay. When they wake up early, they're also cranky. This one's cool. Dave talked about the stair application of this, but what I really like is how they built these guards. So they had a hole drilled through that they would have. This is the base plate, the base cap, and then this was a rod that's bigger that can pass through. This is what's stopping the 2 stone elements from crushing on each other. So these were bearing in between the 2 stone steps, and then this rod dropped down through the assembly to the bottom cap. This one here, you can see that they're resolving the base condition, or that moment, out through a stiffer element that then is resolved by a couple of the 2 screws into the concrete wall. I don't know why this wouldn't need guard requirements of pickets. This code might be very particular. Maybe they installed them and then took them out. Maybe this is an illusion and this isn't higher than 2 feet above grade, although I cannot imagine that. Same with this one. Again, no idea why they don't have to meet the normal guard requirements, but like Dave said, this is being resolved through a couple between this and this. This one I thought was interesting, just that you can start to do interesting things with your pickets. This was just a concept design, so obviously not fully realized, that I found on the internet, but you could imagine you could build into this elements that would meet the requirements for a handrail, or maybe they didn't need a handrail for this particular instance, but you could build this to be a guard very easily. Maybe you could do sub-elements. What are we looking for? Is that from the caterpillar?
Yeah, it's something else. I don't know.
He touched a caterpillar last night, and it's those ones that can get in, like the fibers can get in your skin and make you really itchy. Lots of bug problems in our house. Sorry, it keeps raining. I got bit by a spider over the summer and had to go to the hospital. All kinds of crazy stuff. So here is a glass guard, and I found this on this supplier. They make guards. So they have this one. You can see that they have a connector here and a connector here. So there's our couple, and they connected that. They have that system every few treads to resolve that force at the bottom. They also have connectors into the glass for their handrail. I thought this one was really cool because they've built it so that the actual couple of the glass is hidden in the stair tread. They've come back and capped it all, so you can't even see it. Here's another one, but they alternate how they have this couple coming out. So they have the couple coming out this way here, but look at this down here. They have it coming out in that direction. A little bit harder to detail, but they've done it by saying that point load there is causing it to come out in that direction. This is the one that Dave showed you that he did with Kevin Weiss. a local Toronto architect. So one of the other things is that like we talked about, the continuous top rail. How did Kevin get away without the continuous top rail on this stair?
Roll the dice. It just didn't kind of. Also, the size of the width of one light fails. The width of the opening was small.
So the top rail is about if a panel fails, you don't have a big, huge opening. So I don't know if you could hear Dave off camera, but these panels were small enough that they met the requirement of not being big enough that you needed the top rail to close off that opening. Again, he also said there was some rolling of the dice. Would the building department take offense to this? Again, no one thought this was an unsafe condition, something that the owner was aware of. So this was discussed, and it was determined that this was a safe, reliable system, and the building department took no umbrage with it. A steel plate stair, where there is some connector. So this mostly likely had something welded to it that connected to steel here. So connected in the shop where they were able to grind down and smooth out whatever the connector was. Because when you weld plate steel, you can cause kind of a visual damage on the outside. So they would have done that in the shop and then had the connector be in here that they did on site, so that they weren't welding this on site and then having kind of that chance of an image on the outside. This was some Miami fabricator. I couldn't find who they were. This is on the Sisters of St. Joseph project. I completely even forgot about this guardrail, and in fact found it when I was looking at the pictures, going through all the old images to find all my own structural drawings. So this is a guard of plate steel, connected. Was this? So I didn't do the guard itself. This wasn't my project. I only did the canopy. Do you remember, Dave? Were these pickets or were these posts locally connected, or was it continuously connected to the concrete?
The plate was continuously connected. I don't think there actually are posts. I think that's
right. That's just the welding or shadow lines. Yeah. Okay. So how was it continuously connected to the concrete?
I think it had Nelson studs. It was actually cast in.
Okay, so very similar to what I had just said about this. In the shop, so that they wouldn't see the kind of damage, they welded on elements, and then they held it in place, and it was also the formwork for the concrete along the edge. Here's where you can start to have your infill, and here's where you can start to have your infill. Instead of it being local pickets, you can have it be plate metal that is cut. Here's another one. This one's really cool. It was the same circular pattern cut into two pieces of plate steel, set up against each other, offset from each other, so that sometimes it lined up and sometimes it created these really unique, interesting patterns. You can start to do these kind of plate elements with wood as well. If you can do it with glass, you could definitely do it with wood. You can see that actually this one, they built the frames proud of the wood. So the wood then isn't doing all of the normal guard force. The metal system is doing the guard work, and the wood, even though it's set back from the system, is still really just behaving like the pickets would. Here's another plywood stair. You could do a stone guard. This one was interesting. The description said that it was lime mortar and white pine. I'm assuming that there is some curved wood within this element and then has the lime mortar on top of it. But there is a chance that because of the tight curvature that they did modeling and analysis and actually made this out of only lime mortar with maybe a mesh inside it. Again, I'm not sure. This is trying to back engineer from images on the internet. This is why it's always tough. If you guys ever got frustrated with me when you said, here's my precedent, how does it work? It's not always obvious because the elements are often hidden now. So remember I talked about why it might matter the outward force versus the inward force. This guard would have been analyzed assuming elements were only in tension. So when they're in compression, they're not working for us, and when they're in tension, they are, because they're such thin elements. And so you might be able to make your elements smaller by ignoring the things that by having lower forces for the inward pull instead of the outward pull. Just a few more of the kind of cable guards. And then I found some really cool ones. So Dave showed you this one already where it was fine cables acting as the pickets, but I found a few more cool ones like that. I really like this one. This one actually looked like it is some sort of line. It's not even steel. Now the thing here is the biggest force on this rail now is probably not any of the forces I've talked about so far, but all of these needed to be tensioned. So they probably actually threaded it through and then pulled on it until it was tight enough to meet the requirement not to pass the ball through. But now, as you tighten that, it wants to pull the top and bottom rails together. And that load could exceed that 1.5 kilonewton meters downward that we talked about. And so that could become the determining load case on this guard. This one here, it looks like they actually kept it loose. So this one would have to be analyzed like a catenary. If you put the outward load on it, it will move, and it will move a lot, but there's no place to fall through as long as it can meet those strength requirements. So this one probably was analyzed on flat. They probably built, I'm guessing that they probably did some preliminary structural analysis, saw if it was in the range of it. Then my guess is they would have had to, for the building department, do an actual load test of this, where they would have had to actually load test it for 0.5 kilonewtons over a 4 inch by 4 inch area, but then also, since it's a guard, that 1 kilonewton load. And they probably allowed them to do it over a 4 inch by 4 inch area. And this one looks like it's complex, but it's just that the pickets and the posts are the same thing, and there is a filigree of them. Some rods. Now these were acting all the way from floor to ceiling, and these again might have been tensioned to work for the guard load, or they actually just looked at these guards in bending. Similar on this one, which we showed you when we talked about stairs. So that was the big kind of takeaway. I'm going to add those 2 or 3 slides sometime today, hopefully. And then that will wrap up our guard condition. There is stuff posted about the project. Obviously that was, part 1 was originally supposed to be due tomorrow, or for you on Tuesday. Don't worry about it, make it the end of the week. I'm not in a big panic about it. I showed you my mine was really quick. I expect you to spend a little more time on it than I did, but I showed you an example of kind of what I'm looking for part 1, and I spent 15 minutes making that. So if you spend half an hour making your part 1 submittal, you should probably be doing just fine. Look at what I'm requesting for you. Points will just be assigned to make sure it's all there, and if you have all of those elements there, you'll get the marks. So you should really know what the basic criteria for guards and handrails are: general serviceability recommendations, normal guard material, and standard guard assemblies. And then if you pick a guard for your project element, you're probably going to really want to go back and study this module in depth as you kind of get further into it. And so we'll be recording the Canopies lecture tonight, and you'll see that later.